basically, why not? It's basically the t-test turns into the z-test when n is large, okay? So then you don't have to worry about the degrees of freedom. But the thing I tell you to do, just always use a t-test, because if you have enough samples, it will be
normal?
a z-test, right? So always give yourself a little bit margin of error. So what are the three scenarios we've talked about? We've talked about, so we have scenario 1, 2, and 3, right?
Equal, larger, and then less.
We have h naught, mu is equal to mu naught. HA, mu is not equal to mu naught. H naught, mu is less than mu naught. HA, mu is greater than mu naught. H naught, mu is greater than mu naught.
You kind of mentioned this before, but doesn't the null hypothesis always have an equality in it?
An equality?
Somewhere you
like
might.
This?
Yeah.
Yeah.
I was
Okay.
thinking,
Well, but it's continuous, so basically, it's continuous. So what's the probability of being any one point?
0. I was thinking that the what I'd read elsewhere was that the null hypothesis was always going to be
Include it? Yeah.
include it or be an equal.
Okay, so if you want, but basically, I just write it that way, except basically know that it's probably it's going to be exactly something is 0 if it's continuous, right?
Okay.
Basically, and you're always I could set it up this way. Testing for this, if this is the null, is the same as testing for that. Why do you think that's true?
If it's one-sided, you're.
I mean, I could say this is the null. If this is the null, that's the alternative. I do the same test if mu is equal to mu naught or mu is greater than mu naught. The thing I'm doing is I'm testing on the boundary point. Because if mu is less than mu naught, if I test at mu naught, then if I test at the upper bound, then certainly for anything a little less than that, it's also going to be true, right? Does that make sense? So you test at the most critical value. Okay. I'm testing at the upper bound, because if it's true at the upper bound, then it's going to be true for anything lower. And so what is it that we're actually doing then? When are we going to accept H under this scenario? When are we going to, so then what we do, we get a sample. We get a sample size n. And say we want to do a test. We want to test at alpha is equal. We're going to test at alpha, whatever alpha is going to be. Alpha can either be 0.05, 0.10, or 0.01, something like that, right? It could be any value I want it to be. The thing I can do is I say I want to do it at 0.05, which is the most common one. Then what am I actually doing then? So I get a sample of size n, I calculate x bar. And then I calculate S, okay? Okay, so then I go, So basically what I'm going to do is, just tell me basically what we're going to do. So if I look at x bar, and I'm going to say, okay, let's assume that the mean is truly mu naught, right? Then what am I going to reject? When am I going to accept this? If x bar is what?
Either far below
in
or
general
far
terms,
above.
what am I going to do? If x bar is some extreme value under the assumption that mu is equal to mu naught, then I'll accept this. All right? Doesn't that make sense? I'm only going to reject this as if x bar is really big or really small under this assumption. That's my null hypothesis. That's what my thing is. Does that make sense? Right? I mean, this thing has a t-distribution, right? So if I look at the statistic, x bar minus mu over s over the square root of n, basically that's centered at 0, right? Under the assumption that that x bar minus mu is equal to 0, right? Under this assumption, right? Okay. Then I go, okay, I'm only gonna accept this hypothesis is if I get some extreme value, and that extreme value is based on that. Where nu is equal to n minus 1, right? So, if I find that x bar minus mu naught over f. So if the actual value of this appears in this tail, or it appears in this tail, what am I going to do? Say, well, that's really an extreme value that I saw. So 95% of the time, this should be in here if that's true, correct? If this is true, if mu naught's equal, if the mean of my sample is the same as the mean of mu naught, then I should see this 95% of the time, and I'm going to reject that this is true. Say if I set alpha is equal to 0.05, then this is only going to occur out in the tails here. This will be 0.025, this will be 0.025. So if it occurs out in either one of these tails, it's only going to occur out in either one of those tails 5% of the time, all right?
So if it's in one of the tails, you reject the null hypothesis.
That's right, and I could,
Okay.
so okay, this is what we're really looking at, and then I can write this out. So if this is true, I said, okay, so this is basically implies, or alternately, in one over here, and one reject H naught if what? If
X bar falls.
you know, x bar is, what did I tell, okay, if x bar, if the absolute value of x bar is less than t 1 minus alpha over 2 nu, right? That's 1. 2, we're going to reject H naught if x bar, if x bar 2, I'm testing whether it's less than, so if this is greater than t alpha over alpha 1 minus alpha, oops, t 1 minus alpha nu, right? And 3, well, hope you can see that. 3, I'm going to reject H naught if x bar is less than minus t 1 minus alpha nu. Okay. See all that?
Okay, I see what you did there.
Oh, not x bar. Oops. What should I have written here?
X bar.
Yeah, it would be x bar minus mu naught. No, here it's going to be, because now I'm back in the, I was thinking I was back in the other scale. Which implies that either x bar is greater than mu naught plus t 1 minus alpha over 2 nu s over the square root of n, or x bar is less than mu naught minus t 1 minus alpha over 2 nu s over the square root of n. This one would be or x bar is greater than t 1 minus alpha nu naught plus t 1 minus alpha nu s over the square root of n, or x bar. So a couple of ways you can look at it. This is on the t scale, right? This is on the t scale, the standard t scale, and this is back on the scale of the original data, right? Right, here I transformed it. What's the mean here? The mean of the t is what? The standard t, what's the mean here?
0.
Under the null assumption it's 0. Over here I'm back on a different scale, right?
So the left side is all conceptual, the right side is what we're actually gonna.
Well, yeah, I can test either here or here, right? Over here I've transformed it to a standard t, and over here I've transformed it back into basically, I always do this. In order to get here, first I do this, and then I say, okay, if I want to go back into the original, data, the scale units of the original data, I do the test over here. This is just more practical to see, but actually, this is what you're doing over here. You do this over here, and I get it. If this is true, it applies the same thing. Okay, basically, because this now, I set up the whole test over here, but you remember the thing I have to do is I transform, using this transform. The original data may look like this. Here's mu naught. Now it's not necessarily 0. Mu naught here can be, say mu naught is equal to mu naught is equal to 10. Then I look at my data, and then I'm saying, okay, I want to know that. So basically, what I'm doing is here's my original data. Whenever I collect data, say I look at the sugar content in grapes. Is the sugar content in grapes 0?
No.
Okay, but when I transform it over to here, say I want to know if the sugar, give me, what's the good sugar content? 20, 23, 20, 23, say it's 20, say 21.5. Okay, so we're looking for 21.5 sugar content of grapes. So, okay, so the thing I do is when I wanted to test that, is the sugar content 21? Well, basically what I'm testing over here is I'm saying, okay, here's 21.5, okay? So the mean here is not 0, but if I look at this value, and I get my grapes, I get the, I compute the variance of my grapes, get the standard deviation of the mean that way, then basically, so on the real scale I want 21.5, but if I make this transformation, the mean is now
0.
0. So I set the, now I have a t distribution. Over here I may not have a t distribution. Over here, sort of a non-central t. Over here, it's a central t. I can set everything up nicely, okay? And then I do everything on this scale, the same way we do a z-test, right? I have a normal distribution with a mean of 250. So on a test, I can set up a test there. Then you do is you transform everything to a z, which has a mean of 0, right? And then just transform it back to the original scale again. So that's what I do. I take my original data, u is 21.5, and then I set it up this way. So everything is back, has a mean of 0. I do that, I look at this, I set it up that way, then I go, well, I can test over here. If I pass the test here, it's the same thing as this. It's just algebra to go from here to here. Right?
Mhm.
You got me?
On the right, on the bottom, shouldn't the formula with x bar less than u,
This
shouldn't it be
should
minus?
be a minus sign here. Correct.
Hey, I actually wrote that right.
Yeah, you should.
I'm
I'm just going through this fast.
about joining us.
Okay, so that's the whole thing. I mean, that's basically the whole thing. It looks like the best, but it's really not. So, the thing you're just looking for, you're going to reject the null as if you get an extreme value. That's all it is. And the mathematics of it just comes out to look like this. That's all you're really doing. That's all you do in real life. You go, okay, is this board, say you go to the lumber yard and you're buying boards and you want to get 10 2x4s of 8 feet long. Well, if you go there and you start pulling boards out, and all of a sudden you start pulling them out, and you go, well, they're all pretty close. If you suddenly pull one out and it's 5 feet, you go, huh? It's in the 8-foot section, but it's 5 feet long. What do? Say, this is an extreme value, and you chuck it, right? It's the same thing we're doing here, except we're setting up rules. If you see some extreme value,
Check it.
you chuck your initial assumption that these are 8-foot boards, right? Okay. I mean, if I went there and it says 8-foot boards and they're all 7.5 feet, and I don't have a tape measure with me, I'm just going to start pulling them out and going, well, these look a little bit different, but unless I actually start doing measurements, or say it's 7 feet 11 inches, right? And then I go, I say, well, that looks. I do it, then I get home, and suddenly you build something, and the ceiling is, not the spec. That's when you get screwed. When actually you have a design set, and it's supposed to be something, and then it's a little bit off, and that messes everything up, right?
Yep.
Okay. That's when you really need statistics, is when you start setting things up, and you have to have things within tolerances, and little differences can be
Major.
major. If you're building an engine and you need
Circumference of.
the piston head has to be so much. If they send you all these parts, if they send you the piston heads and you look at it, you go, that's about right. Okay. Well, if you get one that's way off, you get something for like a lawnmower piston head, and all of a sudden you go, well, that's not right, right? You go, okay, you send it back. But if it's really close, then you have a problem. So the thing you have to do is, that's why statistics is good, because you want to get quality control on that stuff, so it will fit. Say 99% of the time. Okay. What else? So we do that. So let's do an example, I guess. Okay, let's go back. Oh. So, is that done yet? It's working.
It's working on it.
It's working. This is pretty. That's why. Okay, that's why I'm having a problem. There we go. It'll eventually come to life.
Nitrogen cycle, carbon cycle, water cycle.
Okay.
Biogeochemical.
Blow it up.
Nitrogen.
Silica?
But there's other cycles
No,
too.
he doesn't care about the silica cycle.
What are we looking at?
This is not geology.
Everything relates to geology.
Just ask right now.
I'm putting.
That's probably what it is.
See, we would be looking for, but those are specific.
And then I guess I
Types.
would say nutrient cycle and water cycle.
Yeah.
There you go, can you see that better now?
Yeah.
What happened here?
It's not-
Oh,
that'd probably
So-
be at least partial credit.
so let's get over here, let's get the CATS data. Remember the CATS data? So we got the CATS data. CATS not found, why not?
It's in the
It's in-
mass.
It's in the mass library.
CATS was?
Yeah,
CATS is in the mass library.
Cats
Cats
and.
and
is
it's
in the
boot library.
Okay, so we'll go over to packages. Go down here to mass library, which I was like, you know what happens on my computer, I have certain things that automatically get loaded. So, okay, we got the mass library, okay, so we got CATS. CATS, is that there? Is CATS there now? Okay,
Yep.
so we get CATS. And then I'll go, names, forget the names of CATS.
That
What
says
are the names of the
mains.
variables in CATS?
You misspelled names.
Yeah, I can't do that right either.
You need.
Okay, so we're gonna attach it now. What did I do? Too many
15.
T's, huh?
Yeah.
Okay, so I attach CATS, all set to go. Okay, so let me go up here and do this. Okay, so the thing I wanna do now is I wanna get, I have CATS, so the thing I wanna do is do a test, right?